Well. Veritasium time. I gotta do it. Dropped 5 days ago. I was gonna react 5 days ago. I didn't do it, but I guess I'll do it now. Because Veritasium drops hot. You know, he drops hot content. I'm gonna just try to keep up with it. You know, because sometimes he be losing me. You know, because this is some complex stuff. It's some very nerdy, like, science, math type stuff, you know. So let's see what Veritasium got in store for us today. 26-minute video. Don't need to make it any longer. The chair needs to stop squeaking. Oh my god, it is driving me nuts. Let's go.
This is a video about the most important algorithm of all time.
Okay.
The fast Fourier transform.
The fast Fourier transform,
FFT. You use
FFT.
it all the time, including right now to watch this video.
How?
And it's used in radar and sonar, 5G and Wi-Fi.
5G.
Basically, anytime a signal is processed, there's a good chance that a fast Fourier transform is involved.
Okay.
But on top of all this, the FFT was discovered by scientists trying to detect covert nuclear weapons tests. And if they had discovered it sooner, it may have put a stop to the nuclear arms race.
How so? I'm sure he's gonna tell us.
I always assumed that the nuclear arms race was inevitable, that once the US dropped atomic bombs on Hiroshima and Nagasaki, it was just unavoidable that all the other major powers would develop nukes. But maybe it wasn't, because it was clear to everyone that nuclear weapons were game-changing. The bomb dropped on Hiroshima released 1,000 times more energy than the biggest conventional explosive, so other countries were rightfully concerned. At the end of the war, Canada and the UK requested a meeting.
They're watching this. Well, no, they didn't watch it, but they heard about it. They're like, what the fuck? They're dropping huge bombs over there. It's not funny. It's not funny. I shouldn't be laughing. I processed it. I processed it too late. I'm sorry. I was laughing at first, and then I realized, yeah, no, it's not really a laughing matter, because like hundreds of thousands of people died that were all pretty much almost all innocent. And, I think that might just be a coping mechanism, to be honest with you. I think you might as well laugh about it now, because it's just like one of those really bad, worst stuff we've ever done, you know? It's just like, we got to get through it somehow.
To discuss what would be done about nuclear weapons. And contrary to what I expected, the US was actually open to these discussions. They realized that they wouldn't be the only nation with nukes for long. So they offered to decommission all their nuclear weapons if other nations would pledge never to make them.
And no other nation pledged to never make them?
This was known as the Baruch Plan. And it proposed that an international body would control all radioactive materials on Earth, from mining to refining to using these materials for peaceful purposes, as in nuclear power generation. But the Soviets rejected the proposal. They saw it as just another ploy to maintain American nuclear dominance. And so, the global nuclear arms race began.
Man! Come on.
To develop new nuclear weapons required extensive testing, and most of it was done in remote places like the Arctic or the South Pacific Islands. The US also created a nuclear testing site in Nevada, the radioactive products of which blew across the country, so that outside of Japan, the people most adversely affected by American nuclear weapons were Americans themselves.
That's fun.
The US soon graduated from fission weapons to thermonuclear bombs, which combined fission and fusion to release even more energy.
Woo! Yeah, that was sick.
Fission and fusion to...
Yo, so look at that. Look, what is that coming off the fucking shit right there?
Release.
Is that
even more...
God damn! Fusion and fission.
More energy.
I'm seeing a lot of cancer right now.
They were as big a leap from the first atomic bombs as those devices were from conventional explosives, 1,000 times again more powerful.
Annihilation of any life on Earth has been brought within the range of technical possibility.
Isn't that fun?
In 1954, at Bikini Atoll in the South Pacific, the US tested a new thermonuclear design that used lithium deuteride as a fuel, and they expected the device, codenamed Shrimp, to release the energy equivalent of 6 million tons of TNT. But they were wrong. It released 2.5 times that due to unanticipated reactions with lithium-7. And as a result, more radioactive material was created and it rained down over a much larger area than planned. Residents of neighboring atolls were only evacuated 3 days later, suffering from radiation sickness. And further east, the 23 crew of a Japanese fishing boat were caught in a flurry of radioactive white ash. And by that evening, they were suffering from acute radiation syndrome. One of the crew died from ensuing complications 6 months later.
As a result of the extended illness brought about by his exposure to the radiation fallout.
These events triggered public outcry against nuclear testing. The modern peace sign was designed in the 1950s by combining the semaphore letters for N and D, standing for nuclear disarmament. A number of world leaders called for a comprehensive test ban, no more testing of nuclear weapons by any state. And this call was actually taken seriously by the world's nuclear powers. They entered into negotiations at meetings with very literal names like the Conference on the Discontinuance of Nuclear Weapon Tests, held in Geneva in 1958. And to show just how serious they were, they even stopped all testing during the negotiations, which is why 1959 is the only year in a long stretch when no nuclear weapons were detonated. But there was a big problem with negotiating a comprehensive test ban, which is, how do you know that the other side will hold up their end of the bargain? The US worried that the Soviets would continue testing covertly and leapfrog them technologically. And the Soviets similarly distrusted the US.
It's like once you start, you can't, there's no going back because you know the nature of humanity. Of course we're not going to trust them, though. Hey, look, if I was the US, I wouldn't trust Soviets either. And if I was Soviets, I probably wouldn't trust the US either. That's just the limbo that you're in. You created this from the moment you started nuclear weapons. It's just like, how do you get out of that, bro? Imagine we never...
So to address these concerns, they convened the Conference of Experts to study the possibility of detecting violations of a possible agreement on suspension of nuclear tests. Seriously, that was the name. I am not making this up.
They got him. They had to have made it short for something.
Now, detecting atmospheric tests was fairly straightforward. The radioactive isotopes they produce disperse in the atmosphere and can be detected thousands of kilometers away. Underwater tests produce distinctive sounds that travel efficiently around a kilometer below the surface of the ocean, and these can be picked up by hydrophones. But underground tests are much harder to detect from afar because their radiation is mostly contained, and the Soviets refused to allow on-site compliance visits, which they regarded as espionage. And this is ultimately why when a test ban treaty was signed in 1963, it was only a partial ban. It banned testing underwater, in the atmosphere, and in space, places where compliance could be verified, but it didn't ban testing underground, for the simple reason that it was almost impossible to verify compliance. But scientists had been trying to find a way to reliably detect underground detonations. Following the Geneva meeting, American and Soviet scientists formed a working group to discuss the issue. And their idea was to use seismometers located outside the countries where nukes were being tested to detect the faint ground vibrations caused by explosions. The problem was, how do you distinguish a nuclear test from an earthquake? Every day around the world, there are close to 300 earthquakes with a magnitude of 3 or greater.
Every day?
300 earthquakes from an earthquake. Every day around the world, there are close to 300 earthquakes with a magnitude of 3 or greater.
That's not even the ones that are less. That's 300. Like, the world is a big place, man. Here in the US, we don't even feel them like that. That's what's fucking crazy. Like, I don't even feel an earthquake. I haven't in a minute. It's like, isn't that weird? I feel like I should be experiencing one at some point. Like, for me to not experience one in so long... I know it's like because we're just not on like the shit with the plates and whatever, but like, dude, it's not a tectonic like.
Part of the purpose of detecting your adversary's tests is to spy on them, to know how big of an explosion they can make. But the seismometer signal depends not only on the yield of the device, but also on how deep it was buried. For a given yield, deeper explosions appear smaller. So scientists wanted a method to reliably determine whether a given signal was a bomb or an earthquake, and if it was a bomb, how big it was and how deep it was buried.
We just want to know.
They knew that
humans just can't go without knowing. We're just too curious. We're curious fucks. We had to know if they were up to something. We wanted to know what they were building and how they were building it, how big it was, because I mean it's
Information.
it is important information in a sense. You have to know if they're continuing the shit, which we know they are. Like, should we be ramping up our shit that we know we're doing, just in case that they're doing this shit that we think they're doing, and we're gonna make sure that we find out if they are doing it with this stuff. It's like we're just a whole bunch of, you know, paranoid, you know, curious motherfuckers.
Contained in the seismometer signal, but it couldn't just be read off by looking at the squiggles. They needed to know how much of different frequencies were present, which meant they needed to take a Fourier transform. A Fourier transform is a way of decomposing a signal into pure sine waves, each with its own amplitude and frequency that add to make it up. This seems a bit like magic, since the sum of a set of sine waves can look arbitrarily complicated and nothing like its component parts. There are some elegant ways to understand how Fourier transforms work. Shout out to the awesome video by 3 Blue 1 Brown. But I want to take more of a...
Hey man, shouts out Mr. Jackson, physics teacher. My bro is always on these videos, bro. 3 Blue 1 Brown. Shouts out 3 Blue 1 Brown. That man even has merch from that guy.
Brute force approach. If you want to know how much of a particular sine wave is in a signal, just multiply the signal by the sine wave at each point, and then add up the area under the curve. As a simple example, say our signal is just a sine wave with a certain frequency, but pretend we don't know that, and we're trying to figure out which sine waves add to make it up. Well, if you multiply this signal by a sine wave of an arbitrary frequency, the two waves are uncorrelated. You're just as likely to find places where they have the same sign, both positive or both negative, as where they have opposite signs. And therefore, when you multiply them together, the area above the x-axis is equal to the area below the x-axis, so these areas add up to 0, which means that frequency sine wave is not a part of your signal. And this will be true for almost all frequencies you could try, assuming you're looking over a long enough time frame. The only exception is if the frequency of the sine wave exactly matches that of the signal. Now these waves are correlated, so their product is always positive, and so is the area under the curve. That indicates that this sine wave is part of our signal. And this trick works even if the signal is composed of a bunch of different frequencies. If the sine wave's frequency is one of the components of the signal, it will correlate with the signal, producing a non-zero area. And the size of this area tells you the relative amplitude of that frequency sine wave in the signal.
He lost me. I'm sorry, he lost me.
Frequency
Fuck
sine
no.
wave in the signal.
I'm not doing all that. No.
Repeat this process for all frequencies of sine waves, and you get the frequency spectrum. Essentially, which frequencies are present and in what proportions.
I'm gonna pretend I know what the fuck
Now, so
you
far,
just said.
I've only talked about sine waves, but if the signal is a cosine wave, then even if you multiply it by a sine wave of the exact same frequency, the area under the curve will be 0. So for each frequency, we actually need to multiply by a sine wave and a cosine wave, and find the amplitudes for each. The ratio of these amplitudes indicates the phase of the signal, that is, how much it's shifted to the left or to the right. You can calculate these sine and cosine amplitudes separately, or you can use Euler's formula, so you only need to multiply your signal by one exponential term. Then the real part of the sum is the cosine amplitude, and the imaginary part is the sine amplitude. In the American delegation at the Geneva meeting, there was a physicist, Richard Garwin, and a mathematician, John Tukey. They got into a debate with the Soviet delegation over which nation's seismometers were superior. So Garwin simulated the responses of both countries' devices on a computer at CERN. The next day, everyone agreed there wasn't much difference. The real obstacle to detecting underground explosions wasn't the accuracy of the seismometers, it was the vast amounts of computation required to Fourier transform the seismometer signals. Here's an example seismometer signal and its Fourier transform. Thus far, I've been thinking about signals as infinite continuous waves, and when you take their Fourier transform, you get an infinite continuous frequency spectrum. But real-world signals are not like that. They are finite and made up of individual samples or data points. Even though a seismometer signal looks smooth and continuous, it doesn't record ground motion with infinite precision. There is some fundamental graininess to the data. So what you have is discrete finite data. So you can't use the idealized Fourier transform. Instead, you have to perform something called a discrete Fourier transform. And one of the distinguishing features of a discrete Fourier transform is that the frequency spectrum is also discrete and finite. You can think of the frequencies as falling into a finite number of bins. And what determines the number and size of these bins is the number of samples in the signal and how closely spaced they are. For example, the more spaced out the samples are, the lower the maximum frequency you can measure, because the samples aren't close enough together to capture high-frequency oscillations. The shorter the duration of the signal, the harder it is to tell similar frequencies apart, so this lowers the frequency resolution. The shorter the signal, the wider each frequency bin is. The lowest non-zero frequency you can effectively...
God, see, this is what I was going to say at the beginning, man. It's just like... I hope somebody watching this is understanding this, because this is low-key all... I'm like getting lost. Like, how does that even like, what the fuck? Like, this stuff, it's just like... it's just so annoying to deal with. Please, somebody watching this. I'm not asking you to explain it to me, because you probably couldn't explain it to me. You shouldn't try. I just hope somebody watching this understands, because I certainly do not. Okay? I'm trying to keep up here. I'm like really trying to focus, so I'm not saying much.
Measure is one whose period is equal to the duration of the signal. And the higher frequency bins are just integer multiples of this frequency, so they fit 2, 3, 4, and so on periods in the duration of the signal. The total number of frequency bins is equal to the number of samples in the signal. So if the signal is made up of 8 samples, then the transform has 8 frequency bins, going from 0 up to 7 times the fundamental frequency. So let's do an example. Say we have a signal made up of 8 samples. Well, then the discrete Fourier transform will have 8 frequency bins. The first bin corresponds to a frequency of 0. Essentially, this measure. Then the discrete Fourier transform will have 8 frequency bins.
Okay.
The first bin corresponds to a frequency of 0. Essentially, this measures if the signal is systematically shifted off the x-axis. You can think of it as measuring the DC offset. You multiply each data point by 1 and add them all together. In this case, they add to 0.
Fuck!
The second frequency bin corresponds to the frequency that fits 1 period in the duration of the signal. So in this case, that corresponds to 1 hertz. You multiply each point by a sine wave of this frequency and a cosine wave of this frequency, and separately add them up. For sine, they add to 0. For cosine, they add to 4. And then repeat the process for 2 hertz, 3 hertz, and
you're hurting
so
my
on
brain,
up to
bro.
7 hertz. And you have the discrete Fourier transform of this really simple signal.
Wow!
Now, this process works fine in principle, and you could use it to calculate all discrete Fourier transforms. But the problem is, it requires way too many calculations. To complete one discrete Fourier transform requires multiplying n data points by n different frequency waves, so n squared complex multiplications. Now, this is doable for 8 samples, but if you had, say, 1,000,000 samples, that would require 1,000,000 squared, or 1 trillion calculations.
A computer can
At the
do that.
speed of
We
1960s computers, that would take over 3 years to complete, all for a single transform. Now, 1,000,000 samples is admittedly more than you would need for a single seismic event, but to analyze tens of events per day from hundreds of seismometers, it would just be far too time-consuming. And that's what gave scientists the impetus to look for a better way. And the breakthrough came in 1963 at a meeting of the President's Science Advisory Committee. President John F. Kennedy was there, as
That guy
were
just seems
Garwin
like
and Tukey.
Yo, that man Art Garwin does not seem like he wants to be there, bro. He's like me, bro, when he was just explaining this frequency shit. That's exactly how I was looking. I was like, man, if you don't get the fuck out of here with this shit. Yeah, I know he's explaining this as carefully and as simply as he possibly can, I'm sure. Like, I just wasn't understanding. Like, bro.
Physicist and mathematician from the Geneva.
I felt like I didn't belong
Although
watching
they were
this
discussing
video.
issues of
I'm
national
like, what the
importance,
fuck?
like the Apollo program and nuclear fallout shelters, the meeting was apparently pretty boring. Garwin observed Tukey doodling throughout. But what he was actually doing was working on discrete Fourier transforms. At the end of the meeting, Garwin asked Tukey what he had worked out, and he was shocked to learn that Tukey knew a way to compute discrete Fourier transforms with many fewer computations. It would mean that the calculation that would have taken over 3 years could be done in just 35 minutes.
Get the fuck out of here!
This has aptly become known as the fast Fourier transform. So here is how it works.
How did Tukey do this?
Consider the example from before with 8 samples. Each of those data points must be multiplied by the 8 different frequency waves.
Okay.
Here, I'm only showing cosines for simplicity. So you would expect this to require 8 times 8, or 64 complex multiplications.
Okay.
But, due to the periodic nature of sinusoids, these waves of different frequencies overlap in a predictable way. For example, at the middle data point, all of the 4 odd frequencies have the same value, and all of the 4 even frequencies have the same value as well. So instead of doing 8 multiplications, you only need to do 2. And this sort of duplication occurs at the other data points as well. So instead of performing 64 calculations, you need only 24. Now, that might seem like a small improvement, but it's the difference between a calculation that scales as n, the number of samples, squared, versus one that scales as n log base 2 of n, which means the bigger the dataset, the greater the savings. A signal with 1,000 samples would require 100 times fewer calculations, and 1,000,000 samples would require 50,000 times fewer calculations. But how do you know which calculations are redundant? Well, take your samples and split them into even and odd indexed points. You still need to multiply each of these by the 8 different frequency waves. But now let's look only at the even points and...
I'm about to step out. I swear to God, I don't belong. I should have said this at the beginning of this video. I'm not gonna understand shit if he starts getting real, like, mathematical on me. Shit. This is getting real mathematical and sinusoidal.
Compare the first 4...
My sinuses. My sinuses are having a problem here because of this video.
Frequencies to the second 4 frequencies.
Cosine.
And what you find is that in each case, at the location of the samples, the values of the 2 sine waves are the same. A similar pattern can be observed for the odd indexed points, except the values of one sine wave are the negative of the other. More generally, they're related by a complex number. But what this means is that you don't have to do all the multiplications for the second half of the frequencies. Once you've calculated the odd and even sums for the lower half of the frequencies, you can reuse these values to find the upper half. So you've effectively cut the number of calculations required in half. But that's only a factor of 2. How do you get down to n log base 2 of n? Well, you repeat the same trick. Split the samples again into even and odd points, and then again repeatedly until you're down to single data points. At each split, you can exploit the symmetries of sinusoidal functions to cut the number of calculations in half. And that is how the fast Fourier transform reduces n squared calculations down to n log n. And it's why today, whenever anyone takes a Fourier transform, it's almost always done as a fast Fourier transform.
Yeah. I mean, a computer
Garwin approached an IBM researcher, James Cooley, to program a computer to run the FFT algorithm. But he didn't tell him the reason was to detect underground Soviet nuclear tests. He said it was to work out the spins in a crystal of helium-3. Cooley and Tukey published the algorithm in a seminal 1965 paper, and its use immediately took off. But it was too late to secure a comprehensive nuclear test.
Who are the nerdy motherfuckers reading this and then applying this? Come on, man. It's just so tedious. Like, who would want to do this, man?
Span. By that time, the UK, France, and China had joined the Soviet Union and the US as nuclear powers. And the partial test ban treaty, far from de-escalating the nuclear arms race, just sent it underground. The thinking was, if you were only allowed to test underground, then you better be testing extensively so as not to fall behind all the other nuclear states. So from 1963, 1,500 nuclear weapons were detonated. That's roughly one a week for 30 years. This testing facilitated the construction of an absurd number of nukes. At the peak in the mid-1980s, 70,000 nuclear warheads were in existence. Total expenditure on nukes in the 20th century is estimated at around $10 trillion each for the US and the Soviet Union, adjusting for inflation. If only scientists had been confident in their ability to remotely detect underground tests in the early 1960s, then a comprehensive test ban could have been reached, stopping the nuclear arms race before it really got going. To check how realistic this is, I asked Richard Garwin himself.
Well, it's a good story.
It is a good story.
It would have helped, and it might have turned the tide.
But that would have required an earlier discovery of the fast Fourier transform. And as luck would have it, it was discovered earlier, but then forgotten. All the way back in 1805, mathematician Carl Friedrich Gauss was studying the newly discovered asteroids of Pallas, Ceres, and Juno. To determine the orbit of Juno, Gauss devised a novel approach to harmonic analysis, and he jotted it down in his notes, but later used a different method, and he never thought to publish that first insight. Today, we can see that Gauss had figured out the discrete Fourier transform before Joseph Fourier himself published it in 1807. And he had developed the same fast Fourier transform algorithm as Cooley and Tukey a century and a half earlier.
No way!
The reason his breakthrough was not widely adopted was because it only appeared after his death in volume 3 of his collected works, and it was written with non-standard notation in a 19th century version of Latin. What do you think would have happened if Gauss had realized the significance of his discovery and had published it in a way that others could understand? With our modern network of seismometers and computing and the fast Fourier transform, today we have the ability to detect magnitude 3 events, which correspond to a 1 kiloton or so explosion, basically anywhere on Earth. Following Cooley and Tukey's paper, the use of FFTs exploded, and they are the basis for most compression algorithms, like the ones that allow you to watch and listen to this video. Here's how the fast Fourier transform allows you to compress an image. You take the pixel brightness values for each row of an image and perform a fast Fourier transform. So essentially, you're figuring out what frequencies are present in the brightness values of the rows of an image. Here, brightness represents the magnitude of each frequency component, and the color represents the phase, how shifted that frequency is to the left or the right. And then, you perform another FFT for the columns of pixels. It doesn't matter if you do the rows or columns first. What you need is a two-dimensional FFT of the original image. For almost all real-world images, you find that a lot of the values in the transform are close to 0. I've taken the log of the transform values so you can see them, but if I don't, then it's clear most of the values, especially toward the edges, are very small. And these correspond to high frequencies. And what this means is that you can throw out a lot of the information in the transformed image, say 99% of it. But when you invert that result, you still get a fairly good representation of the original image. So on your computer, most of the images will be saved in this form as a two-dimensional fast Fourier transform. And then when you want to look at the picture again, the computer simply inverts the transform. There are so many applications for FFTs, from solving differential equations to radar and sonar, studying crystal structures, Wi-Fi and 5G. Basically, all kinds of signal processing use FFTs. And that's why mathematician Gilbert Strang called the FFT the most important numerical algorithm of our lifetime.
Do video games
If only
use FFTs?
it had become more widely adopted after Gauss discovered it, the FFT may have even more dramatically transformed our world.
Hey, man.
Now, I don't think Gauss could ever have imagined how important the FFT would be, just as most people don't think about the cumulative...
It's fun to think about it and all, but he just didn't do it. You know, there's no point in really, like, fascinating over it. The bro didn't do it, okay? You can't blame him for it. I mean, I guess, like, bro didn't... I don't know if he was all about, like, making sure all of his works were published. and making sure that all of his works were out there, because that was crazy. I mean, it seemed like if he figured out the fast for whatever theory, he would have been one of the only people to ever do that. And that calculation could have really helped him out. I mean, he just didn't stop to think for a moment, hey, maybe this might be applicable in other fields. Other people might want to know this calculation and this formula. So why not publish it somewhere and tell them about it? But I mean, he just didn't do it. He had his reasons, you know? And I mean, stuff like that happens. At least we're not all dead right now. But yeah, maybe more people could have been alive if this whole thing was stopped. And the world would be a different place. But who knows? That may be in another dimension, right? Let me know what you guys think. I didn't talk much. I was dead ass just quiet for this one because I didn't know what to say. I didn't understand almost any of those calculations. Like, I was really taken aback right there. I was humbled. I was promptly humbled. When I studied computational science and engineering, that I felt videos was just the right amount of detail for that. It took me the last 20 years to finally understand the FFT as well as you described it here. I recently realized that unfortunately the colleagues are a horrible job teaching the subject. Engineers. I mean, I'm not an engineer. This is for all the engineers out there. Shouts out to engineers. You guys are fucking... Jesus, man. I'm so happy to see that a mathematics video is number 27 in trends. Done real good work in this video. I mean, people like this stuff. I mean, it's good stuff. It's like, this is useful. This is useful for the world. But, hey, man, not me. Somebody else can deal with that. I'm not doing that. I'm glad I'm not fucking forced to do this, bro. Like, I would be killed. Right? Based on the way shit is, if I was forced to learn this, I probably would have been gotten rid of a long time ago. Because I just can't. I'm not the best when it comes to doing this kind of tedious work. I don't know. It's just I can't say it's not for me, but I just don't like it. I don't enjoy it at all. I'm not good at it. I'm not very good when it comes to math. But let me know what you guys think. Subscribe if you want. And I'll see you in the next one. Yes, sir.